In this paper, we propose a real-time NMPC tailored to a legged robot for achieving dynamic locomotion on a wide variety of terrains. We introduce a mobility-based criterion to define an NMPC cost that enhances the locomotion of the high-Q robot while maximizing leg mobility and staying far from kinematic limits. First, we run the NMPC with and without mobility to traverse a pallet. The NMPC without mobility maintains a constant horizontal orientation of the robot's base, hence reaching the kinematic limits in some legs. On the other hand, when the mobility is turned on, the robot pitches while climbing up and down from the pallet to maximize the leg mobility and stay away from the kinematic limits. In a second simulation, we show how NMPC ensures locomotion stability of the high-Q robot by maintaining an essential ZMP margin. When pushed with the lateral force of 200 newtons, the robot falls when there is no ZMP margin. On the other hand, with a sufficient ZMP margin, it walks stably even in the presence of an external disturbance. This simulation demonstrates the importance of continuous replanning at a higher rate. Here, the robot is commanded with a constant forward and heading velocity. Since replanning at a lower rate of 0.8 Hz leads to state drifts due to model uncertainties and tracking errors, the robot walks badly and falls in the end. However, with a higher replanning rate of 25 Hz, the robot walks successfully because it continuously compensates for these uncertainties and errors. We test our NMPC with mobility by crossing a set of pallets, each of 1 meter length with varying heights. Again, the robot pitches as required to maintain the leg mobility. The NMPC is helped by vision-based foothold adaptation, VFA, that provides foothold corrections to avoid collisions, narrow gaps, and the footholds outside the workspace of the swinging leg. In this simulation, we show the efficacy of the terrain-aware NMPC where the robot traverses over rough terrain with a forward speed of 0.3 meters per second. This simulation shows NMPC with the force robustness feature by walking into a V-shaped chimney. When the force robustness feature is enabled, the ground reaction forces stay close to the contact normals, effectively coping with the uncertainties. However, without force robustness, the robot loses balance because of the continuous slippage of the feet due to some uncertainties in the estimation of the normals, and ultimately falls. In the first experiment, we run the NMPC on the high-Q robot to perform an omnidirectional walk on flat terrain. In this experiment, the robot is commanded to walk forward or backward, then laterally, and finally, when the heading velocity is commanded, the robot turns left as well as right while walking. This experiment validates that the NMPC computes feasible trajectories for the robot after receiving different velocity commands from the user while walking. In this second experiment, high-Q traverses a pallet with the help of NMPC with mobility. Here, the NMPC is assisted by VFA. The NMPC provides optimal pitch to the robot to maintain the good mobility and thus to stay away from the kinematic limits. The robot pitches up while climbing up the pallet and pitches down while climbing down from the pallet, preserving the leg mobility during the locomotion. In this experiment, the pallet is pushed in front of the robot while walking. The VFA provides corrected footholds to the NMPC, and the NMPC adapts by adjusting the pitch of the robot's base during the swing phase of the right front leg to attain good mobility at its touchdown.